IBM has spent nearly a decade honing its vision for quantum advantage and large-scale fault-tolerant quantum computing. And now that vision is coming into focus. In 2026, we will see the first demonstrations of quantum advantage. And in 2029, we'll enter into a new era of computation with the first large-scale fault-tolerant quantum computer. We know exactly how we'll achieve it, and we're updating our roadmap to match. Let's take a look. Today's IBM Quantum Roadmap is really two roadmaps in one. Our development roadmap tracks production systems and software tools to enable advantage for end users, and our innovation roadmap tracks experimental work and prototypes that inform production hardware and software, and our journey to fault tolerance. Let's start by looking at how our development roadmap lays out the path to quantum advantage. Last year, we released the IBM Heron, which demonstrated significantly improved gate performance thanks to its tunable coupler architecture, and the ability to accurately run circuits with 5,000 gates. We believe advantage will occur in the next few years if we continue to push our hardware performance and couple it with high-performance classical computing. To facilitate that effort, we're excited to announce a new processor coming in 2025, the IBM Nighthawk. Nighthawk introduces a new square lattice of 120 qubits targeting 5,000 gate circuits. It delivers roughly 16 times the effective circuit depth we can achieve with the heavy hex lattice of its predecessors. This will make it possible for our clients and users to run much more complex circuits and achieve quantum advantage in the near future. In 2026 and 2027, Nighthawk will integrate the meter-length chip-to-chip couplers first demonstrated in our 2024 Flamingo chip, allowing us to scale it first to 360 qubits, then to 1,080 qubits. We'll push the quality as well, with circuit depths reaching 15,000 gates by 2028. However, our users need more than just state-of-the-art quantum hardware. They also need high-performance software to power the next generation of quantum algorithms. Since 2017, we've worked to make the Qiskit SDK the world's most performant quantum software development kit, and we've grown it beyond the core SDK into a comprehensive software stack for running utility-scale circuits on the cloud. In 2025, our latest generation Qiskit runtime engine will improve scalability of dynamic circuits which leverage real-time classical logic to make quantum circuits more powerful. At the same time, our new C API will allow more direct integrations of Qiskit in HPC environments. We'll roll out profiling tools in 2026 and workflow accelerators in 2028 to future-optimize communication between quantum and classical resources. Advancing error mitigation capabilities will be essential for reaching advantage before fault tolerance. That's why, in 2025, we're expanding our error mitigation tools to better leverage HPC and enable more complex workload. In 2026, we'll build on that foundation with the utility mapping tools to facilitate algorithm discovery for quantum advantage. In 2029, we'll provide new circuit libraries for fault-tolerant devices. As we see the first examples of quantum advantage, we'll team up with our partners to expand our functions catalog and roll out a use case benchmarking toolkit to establish standards for advantage in key application domains. Then, in 2027, we'll introduce computation libraries that extend HPC math libraries to efficiently run quantum tasks. Now, let's talk about the journey to fault tolerance outlined on our innovation roadmap. From 2020 to 2023, we focused on increasing yield and solving packaging challenges with the IBM Falcon, Hummingbird, Eagle, Osprey, and Condor chips. We expanded our knowledge of monolithic scaling, showing that we can successfully test a system even with a 1,000 plus qubit Condor processor. To scale further, we need a modular approach. In 2024, we demonstrated Crossbill and Flamingo, which showed our chip-to-chip coupler technologies at different length scales. Now, with a well-formed realization of our quantum LDPC error-correcting codes, it's time to update our innovation roadmap. Central to our QLDPC approach are high connectivity and multi-way couplers requiring non-local gate connections and an advanced automated design flow. We're excited to introduce Loon in 2025 as our target for demonstrating these technologies. Building on Loon will be Kookaburra in 2026, the first demonstration of a module in our fault-tolerant quantum computing architecture. The module includes an encoded quantum memory with a logical processing unit for logical operations. In 2027, we get Cockatoo, which demonstrates entanglement of modules with a universal adapter, all made possible by the long-range couplers first shown in Flamingo. In 2028, everything comes together in a first prototype of a fault-tolerant quantum computer with Starling, which ties together multiple modules with universal computation through magic state distillation. In 2029, IBM Starling makes its way to the development roadmap as a fully delivered, fault-tolerant quantum computer capable of running circuits with 100 million gates on 200 logical qubits. Then, in 2033, we scale beyond Starling to Blue Jay, a quantum computer capable of running 1 billion gates on 2,000 logical qubits. So, zooming out. In 2025, we get Nighthawk and an expanded set of quantum plus HPC tools to help you take full advantage of its increased connectivity. In 2026, we will see the first demonstrations of quantum advantage. In 2027 and 2028, we will expand the variety of problems we can tackle with next-generation computational methods and build a wider range of quantum advantage workflows. And in 2029, we'll enter into a new era of computation with the first large-scale fault-tolerant quantum computer and unlock an even wider range of use cases across industries. We hope you'll join us on this journey.